there's a whisper that has grown into a murmur in the halls of science. A question that strikes at the very heart of our quest to understand the cosmos. Is theoretical physics dead? Some say the great revolutions are behind us. We have Einstein's relativity and the standard model of particle physics. Beautiful theories that describe the universe with astonishing accuracy. But for decades, it seems, we've been stuck. The grand unifying theories that were promised have failed to deliver testable predictions, leading some to claim the field has become a playground of untestable mathematics, a beautiful but ultimately useless game. It's an easy narrative to accept that we've hit a wall, that the well of discovery has run dry. This feeling of stagnation isn't entirely without reason. For a generation, physicists have been chasing ideas like string theory, which posits that fundamental particles are tiny, vibrating strings in higher dimensions. It's an incredibly elegant mathematical framework, one that could potentially unite gravity with quantum mechanics, the holy grail of physics. Yet, after decades of intense intellectual effort, it hasn't produced a single prediction that we can verify with an experiment. This has led to a sense of frustration, a feeling that we might be lost in a landscape of pure thought, with no map to guide us back to the real observable world. The critics argue that the field has lost its way, ruined by its own ambition. This debate isn't just academic bickering, it's a profound question about how we do science. Science, at its core, is a dialogue between theory and experiment. A theory makes a prediction, and an experiment goes out to check if the universe agrees. If this vital connection is broken, then what are we doing? Are we still exploring the nature of reality, or just admiring the intricate patterns of our own minds? The charge is a serious one, that theoretical physics has abandoned its empirical roots, becoming more of a philosophy than a science. It's a challenge that forces us to look closely at what it means to push the boundaries of knowledge. But to declare an entire field of human inquiry dead is a bold claim, and perhaps a premature one. It assumes that the universe has no more surprises in store for us, that the story is mostly written. This perspective, however, misses the bubbling undercurrent of activity, the quiet but persistent work of thousands of scientists who are challenging old ideas and forging new ones. It overlooks the fact that science has always gone through periods of calm followed by storms of revolution. To understand the true state of theoretical physics, we must look beyond the grand, stalled theories and see the new puzzles and fresh evidence that are emerging from our ever-improving telescopes and detectors. To see the lifeblood of theoretical physics, you need only look at the recognition it continues to receive for its profound impact on our world. Just last year, in 2024, the Nobel Prize in Physics was awarded to John Hopfield, a theoretical physicist whose work had little to do with cosmology or string theory. Instead, his curiosity led him to explore the connections between physics and the brain. He developed the mathematical foundations for what we now call artificial neural networks. His work, born from pure theoretical inquiry, laid the groundwork for the artificial intelligence revolution that is reshaping our society today. This is a powerful reminder that the fruits of theoretical physics often ripen in unexpected ways. Hopfield's story is a perfect illustration of why curiosity-driven research is so vital. He wasn't trying to build a better smartphone or a thinking machine. He was simply following his fascination with the complex systems found in nature. He used the tools of physics to understand how a network of simple components, like neurons, could collectively give rise to complex behavior like memory. It's a testament to the fact that the most impactful discoveries often come not from a targeted goal, but from the freedom to ask fundamental, what-if questions. It shows that theoretical physics isn't just about the universe on the grandest scales, but also about the fundamental principles that govern complexity itself. This interdisciplinary spirit is a sign of a field that is very much alive. Physicists are no longer confined to their traditional silos. They are collaborating with computer scientists, biologists, and neuroscientists, bringing their unique perspective to bear on some of the most challenging problems in science. The success of researchers like Hopfield directly counters the narrative of a stagnant field. It demonstrates that the intellectual engine of theoretical physics is not only running, but is also powering innovations that touch every aspect of our lives. Far from being an isolated, abstract pursuit, it is a dynamic and essential part of the broader scientific enterprise. The Nobel Prize highlights a crucial point. The value of a theory isn't always measured by its ability to predict a new particle. Sometimes, its value lies in providing a new way of thinking, a new language to describe the world. Hopfield's work gave us a mathematical framework to understand learning and memory, a tool that has proven immensely powerful. It's a story that has played out time and again in the history of science. Abstract theoretical work, from Maxwell's equations for electromagnetism to Einstein's theories of relativity, has consistently become the bedrock of future technology. The field is not dead. It's planting seeds for futures we can't yet imagine. Just when we think we have the universe figured out, it throws us a curveball. And right now, it's throwing us a big one. For years, our best description of the cosmos has been the lambda CDM model. It says the universe is made of normal matter, dark matter, and a mysterious force called dark energy, lambda, that is causing space to expand at an accelerating rate. This model has been incredibly successful, but new data is beginning to show cracks in its foundations. Recent results from the Dark Energy Spectroscopic Instrument, released in March of this year, have given us the strongest hint yet that dark energy isn't constant at all. It might be weakening over time. This is a monumental discovery, if it holds up. DESI has meticulously mapped the positions of millions of galaxies, creating the largest three-dimensional map of the universe ever made. By analyzing this map, scientists can look back in time and measure the history of cosmic expansion. The data suggests a deviation from what the standard model predicts, a hint that the nature of dark energy is more complex than we thought. If confirmed, this wouldn't just be a minor tweak. It would mean our understanding of the fundamental forces of nature is incomplete. It would demand a new theory, perhaps involving a new particle or even a modification to Einstein's theory of gravity itself. This is exactly the kind of moment that theoretical physicists live for. A puzzle from the cosmos, an anomaly in the data. It's a direct challenge from nature saying, your theories are good, but they're not the whole story. This has ignited a firestorm of activity in the physics community. Theorists around the world are scrambling to come up with new models that could explain this evolving dark energy. Is it a new field permeating space-time? Does it interact with dark matter? These are the questions that are now being debated in seminars and on blackboards, pushing the field into exciting new territory. This isn't the sign of a dead field, it's the sign of one on the brink of a breakthrough. The beauty of this process is the interplay between observation and theory. The incredible precision of experiments like DESI provides the clues, and the theorists then work to weave those clues into a new, coherent story of the universe. The final answer is not yet known, and the DESI team is working to expand their map to include 50 million galaxies by 2027, which should provide a definitive verdict. But regardless of the outcome, the process itself is science at its best, a dynamic, self-correcting quest for truth driven by data. The universe is speaking to us, and far from being stagnant, theoretical physics is listening intently, ready to write the next chapter. Beyond the grand challenges of cosmology, theoretical physics continues to be a fertile ground for bold, and sometimes controversial, new ideas. One such idea is the second law of infodynamics, proposed by physicist Melvin Vopson. This radical hypothesis suggests that the amount of information in a system, its information entropy, naturally decreases over time. This stands in direct opposition to the celebrated second law of thermodynamics, which states that total entropy or disorder always increases. Vopson argues this principle can be seen everywhere, from the way genetic information is stored in a virus to the large-scale structure of the universe itself. Vopson has even applied his theory to the ongoing evolution of viruses, analyzing how mutations in SARS-CoV-2 seem to favor states with lower information entropy. He controversially connects this to the simulation hypothesis, the idea that our universe could be a vast computer simulation. In a simulated reality, he argues, data would need to be compressed and optimized to save on computational resources, a process that would manifest as a drive towards minimal information. While this theory is highly speculative and far from mainstream acceptance, it represents the kind of fearless, boundary-pushing thinking that has always propelled physics forward. It asks us to question our most basic assumptions about reality. Such debates are signs of a healthy, vibrant scientific discipline. The tension between established laws like thermodynamics and radical new proposals like infodynamics is where progress happens. It forces us to re-examine the evidence and sharpen our understanding. It's a process of intellectual natural selection, where ideas compete, are tested, and are either discarded or integrated into our body of knowledge. This creative ferment is the exact opposite of a field that is ruined or dead. It shows a community willing to explore every possibility, no matter how strange, in its search for deeper truths. So is theoretical physics dead? The answer is a resounding no. It is transforming. It is being energized by new data from the cosmos, inspired by interdisciplinary collaboration, and challenged by bold new ideas. From the confirmed impact of Nobel-winning theories to the tantalizing mysteries of dark energy and the speculative frontiers of information physics, the field is buzzing with questions. Our journey to understand the universe is far from over. In fact, it may just be getting interesting. The frontier of knowledge is not a wall we have hit, but a vast open landscape, and theoretical physics is still our most essential guide as we continue to explore it.